All right, everybody. So today we're going to continue our structural masterclass that we have from where we left it at. Although this is a structural class, we are going to learn a lot more than just structures, because to understand how buildings come together, you have to understand every single component within the building and how that interacts with one another or with each other. So this one is a recap of where we left it at. If you weren't part of that class, you can go ahead and watch class 1 of this. But we built this entire element from scratch, explaining the meaning behind each one of these elements: the concrete slab, the foundation wall, the footing, the waterproofing membrane, insulation member, waterproofing membrane, or air and vapor barrier also underneath the slab, insulation underneath the slab. This expansion filler that we put, or insulating filler that we put between the slab and the concrete wall, so that we can isolate that and not have a thermal breach. We spoke about the band joist or rim joist, which has different names depending on the location in the country that you're at, or mud plate, and is a double plate. We have our insulating filler also that connects the concrete with the rest of the framing. And this one right here in green, thanks to Jose Plates, who desire that to be green, is our pressure treated plate that connects kind of directly to the elements. We also went up and put our floor joist at 16 inches on center that would attach to our band joist. We also showed our bottom plate. Our bottom plate seems to be floating right now because technically it doesn't sit like that. It sits right onto our subfloor. So our subfloor right here should be like that, like so. And basically everything sits right on the subfloor. This is what we call platform frame, because we create a platform and then build right on top of it. This right here, again, like we saw, let me just move it correctly. It's our bottom plate, and right outside we have our sheeting. Our sheeting, I grouped it for the sake of making it simple, but our sheeting outside functions as an air and vapor barrier. Depending on what product. If it is a zip system, it's an air vapor barrier. If it is not a zip system, it will need some sort of building paper wrap that will protect from water, and it will also protect from air and vapor. And then lately, we've been seeing conditions in which we actually need to put insulation not only inside the building but also outside, and our siding will come right outside that. We haven't built our siding yet. We will build it soon. Inside our cavity, we have our insulation right here, like you see. And that insulation right here is what gives us the R value. I explained the fact that this insulation doesn't quite get us the R value that it says, because if you see this wall, it is a big percentage full of essentially wood, right? Like these wood members right here don't have the R value that the other piece has. So essentially it's not what it says it is, okay? So, but that's how our insulation gets put in here. Now, there is a distinctive thing about the insulation that I wanted to explain to you very quickly. And it's the fact that bad insulation installation. So there is a lot of theories about, oh, this is how it should be installed, in the sense that the bad insulation has this paper right here. This paper right here that you see, and then you have it without the paper. Quite frankly, the paper functions also as another type of air and vapor barrier. So the correct way of insulating when it comes to that, depending on the location, is to have the paper exposed to you. You should not be seeing the pink stuff, the actual fiberglass. You shouldn't be seeing the fiberglass. You see the fiberglass all the time in a lot of job sites, and you're like, what's going on? It shouldn't be. It's because the air and vapor barrier should be always on the warm side. And in New England, the warm side is going to likely be inside your house. Okay? So in this case, when it comes to the insulating, so this piece right here should be facing into the building, into the outside. This is a different type of insulation, so that's another story. But just when you think about it, always you can study the condition, but just understand that the paper, the craft paper, should be facing into the outside, technically. Okay, there's some really nice diagrams that talk about that and show it. I don't know if this one shows it right, but that should be inside. And not only the paper, but also there's a plastic that they put. So it should be also facing outside. So that's that. Okay, Darwin, here we are. We sized on our previous session this LVL right here. We also spoke about the fact that we do not want a solid zone member here, that we would much rather a lolly column or not even an LVL, because these members right here are wood, and we don't want them to be in contact with concrete. So we do lolly columns or circular columns, which we use a plate right on top of it that gets welded so that it captures the entire LVL to some degree, because this plate cannot just be infinite, right? Like a huge plate that, like if you were to do something like that and you're capturing other LVLs, well, that's not going to be that strong. That's going to deflect. It is a reasonable size. And that's how that member is put together there. I also spoke a little bit about this right here, which you'll see on some buildings, which is a cross bracing that they put, or some sort of blocking. They do it either like that, but they also could have done it in another way, where they literally put a piece of, let me just near. See, so they could literally put a piece of wood. And you probably have seen it at some jump sites like that every certain distance. It doesn't go through like this is the one, but for the sake of explanation, they will place those guys as bracing to protect this element back and forth, just the same way that that cross bracing would do. So that's another way that they do it. So I can show you right now, floor framing 2x10 bracing. You see it right here? This is the way that they brace it right here. This is exactly what I was talking, but that's a rendering. So I want to see a real building, so you guys could see. This is the cross one that I mentioned to you earlier. You see it? So that's the cross. This is the cross right here too. But they do it either with that cross. They do it with metal too. I've seen it with metal. Not as often. I haven't seen it that often with metal. I've seen this one a lot, and I've seen the initial one I showed you at the very beginning of the project. Yeah, at the not the project, at the very beginning of the session. So yeah, right here. So this one I've seen a lot more often than anything else. So those guys help out a lot with the structure. Okay, so we don't often show it in our drawings, but we should probably show it or say something about provide bracing the base. These things are called bays, choice spacing bay, So that's that. So this is a general overview of that. So I'll continue modeling upstairs in a second, but before we go there, let's go back to these elements. So on drawing form, we already know, or bottom plate, or stud, or double top plate, or rim joist, also called ribbon, or bottom plate then again, or stud, or double plate, and so on and so forth. We spoke about our subfloor, which is called sheathing, typically made out of plywood, and the fact that they nail it in each bay like that. Okay, spoke about that stuff. So this book I have also talks about how you frame a bearing wall versus a non-bearing wall. And we're gonna talk about that in a second. So if I was to actually have, for instance, a window somewhere in here and a door, I would have to frame it differently. So I'm gonna real quick group these members and show you how those guys are framed so that we can understand them a little bit better. So I'm gonna just quickly rotate that 90 degrees. I'm gonna move it. So we were framing an area that has a window. We'll still have our bottom plate, just like always. I'm just gonna move this guy right here. And any of you that's wondering what I'm using, it's not SketchUp, it's actually Rhino. So that's our bottom plate. And then we're still gonna have our studs the same way that we've been having it. So I'm gonna just borrow one of the studs right here so that I don't have to make it again. I'll rotate that 90 degrees. And they get nailed to the bottom plate, okay? That's how they get nailed to the bottom plate. So I'm gonna put it right here. There. So you go, you have your studs, and they typically are. Anybody can tell me at what distance we put them on?
16 inches on center.
That's right. We put them typically at 16 inches on center. So we go 16 inches straight that way. Boom. And I'm just gonna now copy a bunch of them real quick. And then I'm gonna copy a bunch more of them to just make it simple for me. Oh, not like that. Copy from here to here to here to here. All right, so that's good. Now, if this wall turned out to have these guys are floating, it looks like, oh my gosh, my bad, guys. I'm sorry. Um, let me go into front view. Let me change the style of the view. Uh, maybe the right view. Yeah, that's completely wrong. They do attach to the floor. You know what? Let me select all of them. Although not all of them are actually like that. It's some of them. I'm not sure what happened. I'm not sure what happened, but they're wrong. So what I'm gonna do is I'm just gonna fake them a little bit. Okay? Do not do that at home. They're not at 16 inches on center, but you guys know they will be at 16 inches on center. Okay. So we have a double top plate right here. Anybody knows why we put double top plate? Anybody knows why we do double?
To make it stronger.
Yeah, so if it is a low bearing wall, it would need a double top plate because it needs to be more sturdy. But yes, so but if it is not a low bearing wall, it doesn't need to be double. So in fact, there's one quick video that a nice lady explains this very well. So I'm gonna try to find that very quickly so that we can take a look at it. It doesn't take much time at all to look at it. Because she also explains more about framing and structural members. And I want to make sure that I'm mindful of your time. Okay. Anatomy. We watched the one about anatomy of a building. Okay. And this is part of our nice benefit to flow members. We have this channel, which is getting really nice put together. So I'm going to make sure I share audio, and you guys make sure that you can hear it. At the count of 1, 2, and 3.
Let's cover a little frame wall terminology. A frame wall is constructed of studs, either wood or metal, and usually sized 2x4 or 2x6. When the stud is placed at the top of the wall, it is called a top plate. The one at the bottom of the wall is called the bottom or sole plate. Vertical studs are placed along the length of the wall, and they are evenly spaced, usually either 16 inches or 24 inches apart, which is measured from the center of one stud to the center of the next. This is called 16-inch on center or 24-inch on center, which is abbreviated as OC. Load-bearing walls may have a double top plate. This is to carry the weight of the ceiling joists and the roof rafters or trusses and distribute that weight to the studs and the bottom plate. However, if the rafters and joists are placed directly above and in line with the studs, then a single top plate can be used instead of a double top plate.
So that's a quick explanation of that, and this video is available for you guys to watch. If it is supporting something, we want it to be double. If it is just a regular frame wall, not supporting anything, we wouldn't want it to be double. Now, when in doubt, you just do a double because you don't want to get it wrong. So you just say, you know what? If it's a double, nobody's gonna get a complaint that you did a double. But if you did a single where you did a double, nobody's gonna complain. But if you did a single where you needed a double, it's gonna be a problem. All right. So or vice versa. I don't think I explained it right. So this is great. The way this stuff works, but now I know why. It was floating because we need the floor. I moved this one by mistake. Okay. All right. So you nail it to that. That's beautiful. That's structurally sound. For the moment you want a window, you're like, okay, what do I do for a window? And how do I maintain it structurally strong? Well, the window, depending on the size of it, will cut through this perfect structure. Like it's a perfect structure right here, right? So the moment you extrude and cut, extrude, not solid, I'm gonna do configuration. The moment you do a hole through your perfect structure, it will cause issues for you because this thing could fall, right? So what do? There are a couple things you need to do. And I want people to kind of understand this. So when you have a wall, there's going to be a thing called a header at the top, and there's going to be a seal. Seals are slightly different than the headers. So what we do is that let me just draw the seal very quickly so that you guys can see it. The seal is essentially another one of these. It doesn't really carry much weight, okay? It really doesn't carry much weight. It just sits the windows right on it. And the windows don't weigh that much. So you're gonna have your seal right here. Sometimes they do put 2 of them. I've seen it done with 2 of them. But that's not really the important member. The important member is the fact that you're gonna need a header right here. And a header is typically made of either 2x10s, 2x8s, 2x12s, or some LVL, depending on the length of the area where you're doing it. So in this case, this header right here. So I'm now modeling it like if I'm taking away from the window itself, but technically it would actually be above because you want to leave what is called the rough opening, right? You want to leave the rough opening clear. This header is going to support all of these studs, which is amazing. So that's beautiful. That's gonna support all of my studs, no problem. In this case, I'm actually gonna split my studs so that you guys can see exactly how this works. Okay. Beautiful. So it supports the studs. Okay. Now, when we're doing structural, one thing I always, and by the way, it's not always gonna be one. It's for likely gonna be multiple members. So in this case, I did that wrong. So there's multiple members that are gonna be there because you just cannot support it with just one. It's not gonna work. So they fill that up with as many as they can. Now that's it. If you sized it just to be the size of the window, how is it gonna be supported? You can't support it. All right. So it needs to be bigger than the window itself. And if this is our window right here, and it needs to be supported by something. Because right now this is floating. This is supported, but this is floating right here. So let's go back to that video where which I shared, because I think that I will start answering some of these questions right as we go. Okay. So building terminology, anatomy of a wall. This video changed ever since that, and you guys watched some of it already.
Center, which is abbreviated, and the bottom plate. This reduces a word that's rarely. The word is fenestration. You're speaking to certain and windows don't inches on center wall.
Okay.
Here is our wall with its top plate, bottom plate, and studs, 16 or 24 inches on center. If we want to put a window in this wall, we have to make an opening for it. So we need to figure out where on the wall it will be placed, and windows don't always line up nicely on the studs. Before we can put the window on the wall, we need to create an opening for it. The opening we'll create for the window, or for a door or a skylight, is called a rough opening, and that uses some additional wood. Of course, we can't have a stud in our window opening, so the load that would have been borne by the missing stud or studs is carried by a piece of wood inserted above the window called a header. The header is basically a beam that is sized to carry the load above the opening that it is spanning. The header is then supported by a stud at each end, and these studs are called jack studs or jacks or trimmers. The jack studs transfer the load carried by the header down to the bottom plate. Full height studs are then nailed to the outside of the jack studs. These are called king studs. The piece of wood that the window sits on is called a saddle or a sill and is attached to the jack studs. We now have the structure for our window's rough opening, and our wall is again structurally sound.
So exactly what you said is what I'm doing here. So I put double in here on the sill or saddle, what you mentioned. But what we're missing right now is that this guy needs to be supported at this edge by a jack stud. And to do so, we gotta kind of make it bigger, right? So you know, this guy's gonna move negative 1.5 inches. And this guy's gonna move 1.5 inches because it's a 2x that's gonna be there. And we can certainly just say you move this way, sole point. And that right there is our jack stud, okay? That guy is technically supporting our entire framing or a header, okay? So many of you may know this stuff, but this is gonna help it be cemented in your brains. All right, so that's good right there. We're good, we're looking good. What do we do now? Well, we need a king stud now. So this king stud is gonna be a stud that will be put there and essentially supports. It still supports or king stud or jack stud because it's helping it. This one attaches to that one, so it helps us. If you see a condition like this, what they're gonna do is that they're literally gonna put them together. Okay, they're not gonna just let it be like that. So remove this one here, here. Okay. And that helps this guy. It's supported by that. So let me just move this one minus 1.5 inches because it's a 2 by. And you guys remember, they're gonna literally move this guy. So this right here. So these guys right here at the bottom are called cripple studs. We have our jack stud, and we have our king stud. And this is our header. And now we're ready to put our window here. If we were to do a door, it would actually be the same thing, but we wouldn't have the saddle or sill plate. We wouldn't have any of these other elements. That's how you frame a window opening area. Now, you would say, well, Darwin, we've done some headers and we've put some bigger posts on them. If the header is so big, this one is actually a pretty big one. You make them bigger and you put actually sometimes a solid 5.5 by 5.5 LVL post, okay, to support it because they need it. They're gonna be problematic. You also use a header like this, like big one, if you happen to have a condition where loads from the upper floor are coming down and you have a window or a door and you don't want to do it like that. So you move them around. And we'll show some conditions like this in a little while, okay? Now, any questions so far when it comes to this rough opening? This is our rough opening.
Yes, I have a quick question, Aaron. In
Mhm.
our drawings, I mean, I just want to make sure when we do the window side, so we give it to the client, that's a rough opening, right? Because our windows have trim. What is it that we give to our clients?
That's a great question. We don't give the rough opening dimensions to our clients. What we're giving them is the window finish dimension. So sometimes we do give the rough opening also. So for that to happen, let me find real quick something in here real quick. So I'm trying to open Revit real quick, although I think it's gonna kick me out. But you're right. So there's rough opening, and then there is a finished opening that finished size that we give. So like if we go to I don't know, Marvin Windows, they have that's not the one. We gotta go to the regional guys. They offer both. They give us rough opening and let me see if I can find. So fits opening size up to 4.5 in wide by 7. So this is the size of the opening, the rough opening, but that's not the size of the actual window. You know what I mean? So if you have a rough opening of 5 foot 4.5 in width by 7 height, they can fit it inside that particular opening. But it's I don't know if they have a spec around here. Catalog. Jesus Christ. They want to get your information so they can track you.
There's something on the top that said technical specifications, maybe that on the top.
Oh, I saw it. I saw it right here. Technical specifications.
Maybe.
Great. This is good. This is good. So, I mean, we can download that. And this is gonna get to another session of the class that I want to talk to you about later on. It's not necessarily just structural, but it's so that when you're doing your drawings, they make sense in relationship to that. So I downloaded it. Where is it? Where is it? Where is it? Okay, so here they give you rough opening. Typically, they use the word RO as a rough opening. Now they're telling you here in millimeters, I think it is, mm. I'm not sure, but that's that. The rough opening is the clear one. Your Revit model will have the rough opening dimensions. You have the option of giving them the rough, or you can give them the regular one. Since we're getting more into specific window types, we actually are giving the client the actual window size. And that's how we go. So you have to check the Revit model and check what the Revit's telling them, and that will be another kind of session. But yes, so the contractor actually wants the rough opening size, so that they don't get it wrong. They typically just want a rough opening size, so they don't care. And this is another thing I wanted to explain. When we're giving building heights, they don't care that on top of this there's going to be another floor. They want the height from the subfloor, from the sheathing, because from the subfloor. Because when you go up, everything comes after. It's like makeup afterwards, so you don't have to worry too much about it. Does that make sense? Okay. So that's good. Now, before I continue modeling my building, which I will, try to do a pretty awesome job on, I wanted to know a particular thing that you guys wanted me to do. Is there a particular condition, a particular beam that you're sizing, a particular thing that you're like, that one, I've never been able to do that. I don't know how that's done, so that I can quickly address it before I continue modeling the rest of my building.
Darwin, I have a small question. So can you repeat the name of the small stud that carries the seal?
These guys are called cripple studs.
Triple studs. Okay.
Yep.
Thank you.
And I do have, before that, let me just finalize the video I was showing you, because she finishes it. So there you go.
However, our drywall installers will not be very happy with the spacing of these studs. So to make the drywall installers happy, we need to put in a couple more short studs whose only purpose is to maintain the on-center spacing of the wall studs. These short studs are called cripples. Now that our rough opening is ready, we can install our window. How does this work for a door rough opening? Well, the process is basically the same for a door. It will have a load-bearing header, load-transferring jack studs, king studs, and upper cripples as needed. The door does not have a saddle or the lower cripples, just the header, cripple, king studs, and jack studs.
All right. So does that help? So that's the name of those, is cripple. These guys are wrong here because I think that when I was making it, I didn't quite fill this void very well. So I'm gonna probably try to split this guy so that we can see them better. All right, so that looks a lot cleaner, much better. Okay, so that's that. All right, so we got our foundation, we got all these elements. Anybody can tell me, what am I missing on this wall right here to continue with my work? What am I missing?
In order to have another level.
Yeah,
The bottom plate.
that wouldn't be the name, but you're on the right track.
Well,
It wouldn't be the bottom plate. It would be the
well,
top plate. We need
I
a
mean,
top. We
sorry,
need a double top plate right here.
I got it confused. So for that wall, it will be top plate, but I was looking at from the other level. Bottom.
Got it.
But yes.
But yes, so we go here, we grab this guy. I'm gonna just basically use this guy right here, and we're gonna come up here, and we're gonna put 1 and 2. If it is, depending on whether it's a structural or not, right? So these guys, just so that I don't want to confuse you, they don't come now. This is not done. Like, first to see, and the insulation also doesn't come. So I could literally hide it because I don't want to confuse you. Right? So that's not there. None of that stuff exists. This is not here either. Okay. And the sheathing is also not there either. And the insulation is not there. Okay, so we got this guy. And literally, this is how they join them too. Like, there's an interesting way of how they join them. Sometimes they need to put more studs right here because they want to close that gap. So they adjust them as needed to be able to kind of join this a little nicer. This is actually not my best drawing on this. So I'm not a contractor. You guys are getting the idea. So we need a double top plate on both sides. And then it appears that if our framing is going this way, likely this framing also is going to go this way. Isn't that right? So what do we need now after we put our double top plate? What's next?
The studs
You mean like grabbing this guy right
yes
here and seating it right on here?
on top. Yes, because we're starting the new wall on the second floor.
Anybody agrees or disagrees with that?
Mm.
I disagree.
Why do you disagree, Felipe?
Uh, I believe, well, you need the rim joist, the band joist too.
That's right. You are absolutely right, Felipe. So what Rai was doing isn't necessarily wrong,
Yeah.
but it's not the right assembly that we're talking about. What she was talking about is called balloon framing. It's another kind of way of framing buildings, believe it or not. And it is a way in which the studs go all the way from the beginning also through, like they sit right on top of each other. Do you see them right here? Can you guys see it? I don't can see it. Can you guys?
Yes.
Yeah.
Mhm.
So that's called balloon frame. There is a problem with that. Anybody knows why they stopped doing it like that?
I do.
Go ahead.
It's a horrible way to do it because the fire will travel all the way from the first level to the other level faster. The way they put the floor now in between is so that it takes longer.
That's absolutely right. You got it. You got it right. So that's good. So let me see if I can do a little.
That was easy.
Yeah, there you go. So that was good. So now what we came up with after the fires that we had in Chicago and also I think in Providence there was another one. A lot of fires happened and they kind of said, you know what, we can't do that. So they come here, they do another band joist right here, and they put it right. Is it right there? There it goes, guys. Right there.
No, to the exterior.
That's right. Here you go. So we put it all the way into our, no, not like that either. Let me move it. So beautiful. So we put it all the way into the exterior like that. And then we need another one on the other side as well. Okay. So this guy comes also right here. In fact, we need one all around the entire space because we need one all around it.
But wait, Darren, I have a question.
Go
I
ahead.
don't think that isn't that one called the rim joist because it's exterior. It wouldn't be the bend joist.
So at the beginning, we mentioned that band joists and rim joists are pretty much the same. It is this thin that goes all around. But in one of our videos, we decided that we were going to be calling these guys right here band joists because they go on the opposite side of the framing, like parallel to the framing. And these guys were going to be called rim joists. But to be honest, you can call them either way. Just don't have a drawing that calls one rim and another one band. Just use the same for both of them. Okay?
Got it.
Perfect. And that brings us all the way back. We already saw how to frame our wall. Yeah, there you go. So that brings us back to this drawing right here. They say rim when it goes perpendicular to this guy, but they often say band joist when it goes parallel to the guy. So let me see if I have another option. Maybe not. This is a little slow. I'm not sure why. Okay. So here we go. So now we got to put our floor joist. Okay. And often in the houses that we work on, we learned that this guy cannot go all the way from here to I copied something else. So So from here all the way to here, they can't. Anybody knows why they can't go all the way like that?
Aren't we supposed, because we're supposed to have the inner pin joist that aligns with the wall? I
Nope.
believe.
The
No.
reason
Es una
why,
distancia muy grande.
that's right, because it is a very long distance, and this little
Oh,
2 by
yes.
8 is gonna fail. It's
Va
gonna
a
go down.
afectar.
Okay. So what we've seen done a lot in a lot of the properties that we've worked on, what we've seen is that they literally build walls, demising walls in our buildings. If I can find my line. I just drew a line. Where'd it go? I don't know where it went. Let me just draw another one. It's still not there. I can't find it. Let me. I don't even want to have anything to pin into. So I'm gonna turn all these guys off. Intersection. Well, long story short, they will build walls right at the location where these members will go so that they can support them. Okay, so that's what they did. So they would build these walls, and these guys could be supported like that. Now, they didn't, and yeah, the wall wouldn't be that tall. And I'm doing like a big solid wall, but in reality, you know what? I'm not. I'm gonna be truthful to the fact that we're teaching structures in here. It would literally be one of these, but made out of another size of material. Anybody knows what size of studs they will use on that?
To support the beam
What size do they use inside? Right here.
for the regular walls, 2x4.
That's right. So these guys will be 2x4s. Okay. So these guys will be made out of 2x4s. Now, these still wouldn't be sitting like that because it's too long. It's not the only reason. Anybody knows another reason why these guys wouldn't go all the way from here to there? I think I said it earlier.
Because the span is too long, so they cut
Well,
it
the
in
span is too long, yeah, but now it is supported by a wall. So why do we still need to? Why can't we have this one still?
It's expensive, so I think if the point of cutting it is so they don't have to pay for a whole entire member, but rather half of the way.
Well, the other reason is not so
Uh,
much the fact that it's expensive.
that was,
Felipe, you were
yeah.
gonna say it?
I was thinking about the tributary width. So
Really nothing to do with the tributary width. The reason why they wouldn't be able to have this guy go straight are two. One, you can't find them like that. They're not that tall. You can't find them like that. Members, it's made out of wood, guys. It's a tree. So you can't get a piece that's gonna go from here to like 30 feet from one side to the other. It's impossible. Okay? So in fact, we can ask our really good friend ChatGPT, what's the size, typical size, longest size of a 2x10? Well, 12 feet, 17 feet, 18. But that's just how much they can support, is that's what he's telling you. But I'm just saying, how long do they make them? That's all I want to know. So lumber length come in length of from 8 feet up to 24 feet. These, although Rai didn't know it because we didn't do it with her, is actually very long, right? This from here to here is 30 feet. Okay, so they don't make them like that. So what do? They cut them. They literally just cut them. So what I'm going to do right now to illustrate this is show you exactly how they do it. Let me just draw from here to down there some sort of rectangle, planar surface, and let me just use it as a scissor to cut these guys. Okay, split you and you using you. Okay, so these guys are not only being cut, the other thing that they also do is that they move them around like that. And not only do they do that, they also do this. And they join them together. Okay? They go one past the other so that they can connect nicely. Have you guys seen a condition where these members are like that, crisscrossing? Have you seen that condition before? Natalie? Maybe not. Okay. But that's how they do it. So in most of our projects, guys, that we get hired to create an open concept kitchen, Rye has done a lot of them. This wall that divides the kitchen area, let's say the kitchen is on this side, from the living room area, it's literally supporting a bunch of members like this. I'm going to group them. And we need to then come up with a way of actually fixing it. Okay, so that's it. So what do? Well, they, I'm gonna explain to you how they build this so that you can kind of interpret it a little bit better. And I think this is gonna be very helpful. So let me just quickly do that. All right, so they have their wall right here. These guys are at 16 inches on center. These guys are at 16 inches on center. This helps this member transfer the loads all the way down to the foundation right here. You see that? All right, so they're all that. So here we go. The client calls us and say, hey, Ryan, hey, Darwin, I want an open concept kitchen and I want to be able to get rid of this wall. Can I get rid of this wall? And just say, no. Why? Because this wall may be structural. Why? Because joists don't go all the way from this side to this side. So if you take that guy, it's likely going to fall. So, and we have an example of a project. I think Felipito went to measure it yesterday that literally we're going to do an open concept for. Sylvain. I hope Felipito has saved the files in the right folder because I get really picky about that. And yeah, he did. Good job, Felipe. So this house, okay, this house, you guys can see that. They had a chimney here, by the way. They took it down. They should have been careful when they took it down. These ceiling joists are sitting right onto a wall right here. Right here, this wall. You see this wall right here? If they took that wall down, this ceiling will fall down. In fact, they've already taken way too many studs. If you think about 16 inches on center, 1, 2, they might have taken 2 studs off of that. That's very dangerous. Very, very dangerous. So they've taken the studs down and this thing could fall. So what they will need to do is that they will need to, prior to demoing this wall, create a dummy wall and another dummy wall and support this joist temporarily. While then they could demo this piece. Why can they demo it? Well, because this is being supported and this is being supported. Great, beautiful. And then what they're going to need to do is call you guys to size an LVL. And that LVL size will vary, but it also will be going right here. And it's going to need to cut this joist. They cut this joist and they're going to need to joist hang them. split this, 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 using this. Group. Oh, I didn't split it. Didn't split it. My bad. Didn't. I don't think it split it. I don't know why. But these guys need to go split. I don't know why. I'm having a hard time understanding why this thing's not getting split. But that's how they would do it. They would then put these guys, and then so what are we missing now? Okay, we put this LVL here, and we have this window here. What are we missing now to be able to complete our new LVL?
It's floating. We need columns.
Exactly. So we're gonna grab this member right here. Whoop. And that member is problematic because it lands on a window. Is that right? So that member will need to be supported by the header. And that header, in this case, we have a header. We happen to have a header. But if you didn't have one, you will have to size the header. But in this case, that header, and we don't know if that header is actually sized correctly for this member right here. Okay, so we don't know that. And we're gonna be pulling up or Revit World, or a structural software in a minute. Yeah, we're gonna be doing that in a minute so that we can see very quickly. I'm just gonna put what this looks like. But yes, right is absolutely correct. We need one piece like that, and we're gonna need another piece like that on the other side. Because it cannot just go infinite. So they typically tend to line up perfectly with the columns below, which we just created. Jose was asking me, and then once you've done that, these guys go away. And you're like, what? They build that wall for nothing. They just, it's temporarily, it's just 2x4s. It's nothing crazy, right? And then, they do that. So we're going to be needing this guy right here to help us support this header, likely better than the one that we have. So now we're faking this thing up a little. So you guys get the concept. I want you to get the concept. I can hide those guys if I want to. But I'm not going to do it. So I'm going to hide this one and this one. All right, so that's been supported like that. This load's being transferred right here. Let's say this is a colonial style home. So we're going to have a roof right here, right? Falling into here. So there's like an attic basically. So we have to think about what does that look like. So that's going to come next in a minute. But this is our ceiling condition. And now we have our LVL, and we've resolved our problem with this piece. So how do we know that this header right here is correct for this particular member? And how do we know, how do we calculate this thing? Because we have to calculate this LVL. Then we have to calculate a column that's going to support it. Then we have to calculate a header that's going to support it. And then we have to calculate posts that are going to support it. Are you guys ready for this? Do you guys want me to size these members right now for you, live with you here? Raise your hand if you are. And we'll wrap it up right after that because I know people got to go home. But anybody?
Sure.
All right. Okay. I didn't feel the encouragement, guys. So
No, no, no. Times no.
I don't feel the encouragement. I'm sorry. But I'll go anyway. We'll try. We'll try. Now I feel bad that I actually I keep doing this thing of like taking members from one side to the other. This guy is still here. Okay. We don't want to lose that guy. A little lower than that. All right. So the way that we go about it is, and this is another question I had. People were asking me, like, how do I do the framing plan for something like this? Like, hey guys, the framing plan is essentially, and I'm gonna use a concept called clipping plane. The framing plan for each particular floor represents what's on that particular floor. So if I'm saying first floor framing plan, if I'm saying first floor, second floor framing plan, well, second floor framing plan is that. Okay? If I'm saying this is actually wrong the way it is, I'm gonna flip it. 90 degrees. No, 90 degrees. 90 more degrees. Because that's a section. So if I'm saying first floor framing plan, it would be looking at this guy without the floor. Okay? Like that. That would be my first floor framing plan. Literally looking at the framing plan. If you go to the basement floor plan, like a structural plan, you're gonna see the basement foundation, but we're gonna be seeing these guys in dashed lines, and we're gonna see the columns and the columns solid, and the footings. Okay, if we're gonna go up and say second floor framing plan, you're just looking at the second floor framing plan. Disregard the rest, just the second floor framing plan. Okay, and if you're gonna do a roof plan, in this case, you don't have one, but it will be looking at the roof only. Okay, hope that makes sense. All right, so how do we size this baby up? Let's do it. Let's do it from scratch. New project. We're gonna call this flow test. If it lets me type, doesn't let me type. Something is wrong with my computer today. Maybe it needs a break. Yeah, something is certainly wrong with this. Well, this thing decides. Let me just peruse it through this. It's good. Look at the studs right here. Look at your bottom plate right here. Good. This is balloon frame, like the one that Rai was saying, I think, by looking at this right here. It looks like it is. All right. Anything else? Anything cool? You didn't go to the basement? See the basement. I want to see the basement. Yeah. Cross bracing. Anybody can see it? Cross bracing right there. They also have the regular bracing too. Solid ones. This thing's strapping right here. We're going to talk about that later. They were attempting to finish this basement with studs. We didn't do it. Look, or LBL right here, or column in LBL right here. But we have a flush frame at the top. Okay, that's the difference. Very good. Let's see if this guy, okay. I think now we're good. Flow test. All right, so what are we gonna do? What I like to do is collect some data very quickly. I wanna know, these guys are gonna be, so this is 30 feet and this is right in the middle. So this guy is 15 feet and this guy is 15 feet, right? So we're gonna go into a floor joist right here, floor joist. And we're gonna say 15 feet span, great. And we're gonna use solid zone. And they're gonna be, I believe these guys are 2x8s. So let's just confirm it. Distance. Actually, these are 2x12s. Not bad. Not bad at all. So these are 2x12s. So we're gonna go here and say select structural 2x12. At 16 inches on center. A path. Great. Beautiful. 15 feet. So then we save. And then we're gonna size our beam. Uniformly loaded beam is the way to go. So you find uniformly loaded floor beam, and I'll show you the difference between one and the other. So the first thing I want to know is how long, span length, how big, how long. So, okay, how long? Well, I'll tell you right now. It's gonna go from here to here. 14 feet 8. By the way, if something is 14 feet 8, you grab the 8 and divide it by 12, and it's going to be 14.666. Okay? So you divide the inches by 12, and they turn into decimal feet. 14.6. So you're going to go into your member, and you're going to say 14.666. That's the length. In my case, I would want to just say 15 because it's longer. Now, if you go and say equal, oh yeah, it passes. Well, of course it's passing. You didn't give it any load. You only change the span length. So the first thing is change the span length. The second thing is you're going to figure out the tributary width. The tributary width. It has two sides. Why it has two sides? Well, because it's supporting size 1 and it's supporting size 2. You guys see that? So what is the size 1 and what is the size 2? Anybody knows what the tributary width of this is, knowing that from here to here it is 30 and that it is sitting right here in the middle. What will be the tributary width on the left and the tributary width on the right? Anybody?
7.6.
Anybody else?
Wait, what's 1/2? What's the full half?
So this thing from
The
here
whole thing. Mhm.
to here is 30.
It's 15. Because it's the tributary width is half of the left and half of the other side.
Pero está agarrando la mitad de la parte 1 y la mitad de la parte 2.
Yes.
So Natalie, do you agree that's 15 or do you agree that's 7.5?
7.5.
Espérate, Darwin, I get confused. What's one side? The whole thing.
So this is size 1 and this is size 2, and you gotta load the tributary width that belongs to this member onto it. What's that width?
No, I wanted to know what's the entire thing so I can do the half. Like what's from the bin to the other side.
So I said that from here
Mhm.
to here is 30.
Oh, I get it.
Anybody changes their mind? Rai says 15, Natalie says 7.5.
No, I'm changing that 1 second.
7.416666.
Yeah, 7.5, but we have to do the decimal thing that you said.
7.41666666.
Right, so you guys are all saying that the tributary width is going to be 7.5.
Mm-hmm.
Okay. Tributary width 1 is half of the length of this side, and tributary width is half of the length of this
The other
side,
side.
because the other half is being supported by or
The
put
wall.
nice, beautiful studs. Okay. So that's our tributary width right here, 7.5, 7.5. Now, right, I think I like that you double checked your math and that you sat down with the calculator or something. But just so you know, it's half of the half of the half, basically. So just say, well, 30, 15, 7.5, right?
Yeah, I just didn't
Or-
hear
or-
the whole thing.
Yeah,
First.
or I guess you could say 30 divided by 4, right? Because this guy is it's gonna basically divide it into 4 areas. So 7.5 will be the tributary width. This member is only responsible for carrying half of that load. And how do we know that? So we go here into our structural software real quick, and we load this side with 7.5 and this other side with 7.5. Now, I did explain it on the previous class, and I encourage anyone that didn't watch it to watch it, because we did a beam like this. But I want you guys to understand where these guys come from. These members, these numbers right here, this right here, it's not something I made up. These are floor live loads for a living space that has beds, bathrooms, things like that. And these are floor dead loads for a place that probably will also have walls and the load of its own member, right? Like the actual beam weights some, right? So they do that and they quantify it as part of the tributary area. And they say, well, 40 plus 15 times 7.5 will tell you what the tributary area is, what the tributary width is. So like if you get We did it in math, so last time I wasn't so great at it, by the way. So, but it actually was accurate at the end. So every square foot of this thing will be multiplied by 45, essentially. So like if you get the area, we're gonna do that real quick right here. Like if you get the area of this thing, you say area. So this thing has 102 square feet, this thing right here. So 102 square feet, 102 times 45, it's 4,590. That's gonna be the weight that this member right here is actually not 45, it's actually 55. So let me just you remember 40 and 15. So it's actually 55. So 100 and let me see that. So 102 times 55. It's 5,610 pounds. That's the amount times 2. This thing is going to be supporting 11,220 pounds. O sea, I don't know if I explained it. I almost spoke Spanish. O sea, what I mean by that is that this whole thing right here is 11,000 pounds. So 11,000 or so pounds, 11,220, because it's a tributary area, and it already includes the dead load and the live load that's going to be sitting on here. So that's it. We come here now. Now you understand. And this comes from the building code. Okay, this is where it comes from. So I can show you in another session where that comes from. But this comes from the building zone. So you go into the solid zone, and you know for sure not solid zone will ever support this thing. Like it would just not do that. So if you go to the solid zone so that you can see how horrible of a failure it will be, you could try the 2x12, like 3 of them. Select structural and say equals, and it will fail. It's way too much. It will fail. Okay. So we immediately go into the LBLs. That's why we go into the LBLs, because those guys can do it. And we have an 11 and 7/8. We already kind of did it in our thing. So it passes by 12%, which is not too bad. Not too bad. I would want a little more if it was up to me. 3 members, 1 3/4 by 11 7/8 passes by 12.6. Okay, you know what? I'll take it. But ideally it will pass by more. Okay, just so you know, ideally it will pass by more. So here we go. That's the disguise. That's all good. That's all good. We already sized it, and you're like, okay, Darwin, we sized the ABL, but now we have to size this post right here. How do we go about it? Okay, we go on to posts, columns. And of these columns, we're going to load it, going into actual load. You have to save first, actual load. And you're going to pick, you see why you have to save? These guys don't show up unless you save. You have to go back and save. Every single step, go back and save. Okay? So once you save, you're going to load it, going to actual load, and you're going to pick one or the other. It doesn't matter. Doesn't matter, A or B. You know why it doesn't matter? The load that this guy is carrying at this point is the same load that this guy is carrying at this point. It's tributary. It's distributed through the whole thing. So it doesn't matter. Okay? Does that make sense? Because by the same token that these guys are half and half, well, this end is going to be half and this end is going to be half. Does it make sense? Anybody?
Yes.
All right, so you pick any of them, doesn't matter. I'll pick B because it's on the right and the whole thing's on the right. It wants to ask you if you continue loading it. You're going to say no. There's no more load onto it. And how much was the math of load that I said that this whole thing was carrying altogether? 11,220? Is that right?
Ajá,
You see the load right here?
la mitad.
Exactly. So the actual load is 4,500. The other one is 1,825. It is carrying about 5,000, actually 6,000 or so. So it is carrying all of that. Okay. So it's carrying half of all of this load. That's how you know if your math is right. You can actually be tracking your math. So if you divide this by 2, 5,610. And this is a little more. You would say, whoa, what's going on? Why is it more? I think it's also carrying the load of its own column, on it. So likely. But I don't know. So that's this guy. So then you're gonna go to design and you're gonna pick a member. So we always want square members. We don't like non-square members for columns. Okay. So 5.25 by 5.25. Yes. It passes by 78%. We have a winner. Okay. You have a question, right?
Yes, I think it was on the structural LBL, but we don't, I mean, we do that, but not in all cases. Shouldn't it be Douglas very large if it's a regular column?
Yeah, it could actually. You are right. So you are right. I went immediately into the design element and I went into the LBLs because I wanted to connect an LBL, which is a similar material, with another LBL, which is a similar material, but also because I wanted to play it safe. But it is not the most cost-effective way. So you can go back and say solid zone, and you could, here, listen to me, you could put 2x6s. Literally two 2x6s together. You see how they're showing? Two 2x6s together next to each other could almost support this thing. Now, this is failing by 125% with 2x6s. So let's see if we do select structural, if it gets any better. Still failing. So the 2x6s together, you could probably try three of them. Let's see. 3 of them passes. So this is something that contractors are going to tell you. Hey, what if I put 3 2x6s together? They have to make sure they nail them together. This thing's telling you that they got to be nailed together. Okay. So, and there's a lot of tools in here that you can mess with, by the way, but we're not messing with them right now. But if they put 3 2x6s together, literally 1, 2, and 3, better than what I showed it, like together. Okay. They could do away with that guy. And they can do this guy. Okay, like that. That will do it. Okay, that could do it. Same thing with these sizes too. They could probably do it. So now what comes next? We're gonna size this member right here. But this member, it's not only carrying this wall, it's also carrying this stud. So it gets a little complicated. So you guys are gonna learn something new right now. Okay, if this right here, this area right here. So let me see, do edge. Length. So this thing right here is 13 feet long, by the way, this thing right here. So if this thing right here, right, this thing right here, this header is not only supporting this piece with half of that load, it's also supporting this wall. So we got to talk about that. That's going to be a new thing for many of you that you've never done before. So now we're going to go and we're going to size our header. What's our header? It's a uniformly loaded beam as it relates to the wall, but we don't want to do a uniformly loaded beam. We do not want to do a uniformly loaded beam. Okay, for headers, you do not want to do a uniformly loaded beam. Or at least not on this one. If it's a header, so let me retract that. So if it is a header, if it's a header that's supporting this joist, like right here, you could figure out how to do a distributed, like it will be just like a beam, okay, with only one side instead of two tributary areas. Does it make sense? Hello?
Yes.
Yes, it does.
Yeah. So this guy right here, it's not supporting the joist. It's only supporting this beam, half of it, this column with all of the load of this column, and it's supporting this wall right here. So we're not gonna use the uniformly loaded. We're gonna use a multi-loaded multi-span. We're gonna come in here. What did I say the width of this one was?
13.
Yeah, let me see, length. Yeah, it was 13. Thank you, right? So it was 13 feet. So you're gonna say 13 feet. Great. Okay, Darwin. We got this guy. What do we do now? It's going to have a point load, guys. Can you see that this guy right here is actually a point load? Let me group it. Yeah, so that point load, it's gonna have a point load. So you're gonna have to come here and say point load. And you're gonna load your column and say A. And we can just say no so that we can see it. But there's a problem. It's showing A aligned with A, and it's not right. That's not what's happening. We don't have it at the edge. We have it like at the middle. Okay? So we have to figure out exactly where that point load is, because this is wrong. This will be wrong. You will fail and this thing could collapse. Okay? So you do not want to do it wrong. You want to make sure it goes in the right location. Okay? So we come in here and we figure out the location of this member as it relates to our Rhino model. And what I would suggest is that you come here and do a distance from this edge to the middle of your stud.
008, 6.6.
I mean, it wouldn't be in the middle, though. I think it's wrong. 7.4. Actually, it's almost in the middle. No, it's not in the middle.
It's 6.5 if we were doing tribulatory width, but because we have to go right in the middle, it will be a little less, like Natalie said. Like 6.
Yeah. No, it will be right here. Whatever it is on our opening, because our opening is not center.
Yeah. Oh.
6.5.
So it would be 7.4. 7.4. No, no, you're not understanding it. So 4 divided by 12. I'll explain it in a second. 1.3. So this guy, it's not in the middle. You see it? So you can't do the half of the 13. You have to put exactly where it is, from one side to the other. I always start from the left, and it will be a 7.3 of distance. So you come here and say 7.3 feet, and you see how he puts it right there? It's not in the middle. Otherwise, it would have been, 7.5. What is it? No, 7.5. Half of 13 is 6.5. So it would have been 6.5, but that's not what it is. 7.3. It's different. All right. So do we just size it now and we're done, or are we missing something else?
Like something. Sorry, something else to change in the structural system, or you mean like another?
Are we missing any other loads onto this member? So if we come here and study it, we have this guy sits on this, goes down, and he sits on this header. Is there anything else sitting on this header that we need to compute that will be critical to it? Yes or no?
The top. It's not cripple, but like those top ones.
It is called cripple. You're actually right. Those are called cripple. And yes, they need to be computed. So what you do is that you figure out the height of them. Let's say 4 feet. If he ends right here, 4 feet, and you're gonna go to walls, and you're literally gonna create a 4 feet tall wall out of 2x6s at 16 inches on center. That right now is carrying nothing. Okay, that right now is carrying nothing. We don't know, but for the purpose of this, you gotta go back to this guy, and you have to load that wall onto your member. And now you have a distributed load. It is a distributed load because it's distributed across the length of this element equally. Does it make sense? And now is when you finally can actually say, okay, what size member do I need? But you have to always go back and say, well, is there anything else that's sitting on this guy? And you would say, well, Darwin, it's easier because you're actually doing it in 3D here. But remember, you guys are doing these things also here in 3D. So you could actually think through them when you're doing it. You can say these elements are all 3D elements. You can go into your Revit model and try to understand it. It's not to the same level of detail. It's not, but you start understanding this, guys. Okay. Right. So now we can actually go and size it. And we go into our members and say, well, you know what? Solid zone is what we're going to do. Let's do 2x12s and let's do like 3 of them. It actually may pass, to be honest. Oh, and it's inadequate by 162. Let's say we do select structural. Oof, is inadequate by 57%. We got to go. We can't, let's see if we do 4. Inadequate by 18.6%. So this header is just not passing with a 2x12. You have to go into the select structural. And of course, any nice little, even 7 1/4 as select structural, 3 of them will do it because they are a lot stronger members. This one didn't do it. Well, it's not doing it. None of these members are doing it. This is interesting.
2x10.
Yeah. 9 1/4. Let's see. Okay, getting better. 9 1/2. Getting better. Yeah, we got to go all the way to 11 1/4. And then that passes by 33%. Okay? You see, you couldn't just, so this thing is actually wrong right here. This member is wrong. It's not the size that we need. We need 11 1/4. Let me see what system. Actually, this may be right in the sense that it is the right length. Yeah, it is the right length, but we color these guys differently because these guys are LBLs now, right? That's an LBL now, right? They have a different color. I insist that this guy should have been an LBL, but I'm not gonna fight that, okay? Because this guy should be. It just looks better when all of the members are the same color, like easy to look at. You know what? But you guys know that 3 2x6s do it. All right, so now we have to size these members and these members. Sometimes I don't do it because if this triple 2x6 can support half of all of this, well, just put 3 2x6s in here and call it a day, right? Anybody? If these 3 2x6s can support half of all of this load, can 3 2x6s support half of all of the load of the header? Maybe, no, yes, I don't know.
I'm not sure.
Yo por igual.
No, sure. Okay, so right now I'm carrying. Hold on, can you mute yourself? Right? Yeah. So right now, this baby right here is carrying. Baby is carrying. So right here, we have baby Rye, baby Natalie, baby Jose, baby Platis. This 4. But this column is only supporting baby Jose and baby Natalie because this other column is supporting Felipe and Rai, right? So this column is supporting baby Rai and baby Jose, right? So we're good there. Baby Rai and baby Jose. This header can support baby Rai, baby Jose, and a little bit more. Because this is not a whole lot of load. These guys are not a whole lot of load. They're just very little. So now this guy is only going to support Rai, and is only going to support half of these guys right here. And this guy is going to support only Felipe and half of this little load. So if this guy can support the whole of Felipe and the whole of Rai, can this guy support only Felipe and a little bit of this whole? If he was to be the same.
Yes.
Does that make sense now?
Yes.
I hope that the illustration doesn't make any of you feel bad. You all weigh the same for the purpose of this, okay? But yeah, guys, yes. So this guy is supporting half of all of this load right here. So if you use the same member for that, it would certainly pass. So let's look at that in actuality, okay? Let's look at that in actuality. So we went back to our column, and our column is 3 3 2x6s. Okay, select structural. So now we're going to create another column made out of the same materials. Okay, 3 2x6s, select structural. And we're going to load half. I got to save everything. Hold on. Save it. Oh, I did a wall. My bad. You saw that, what I did? You guys notice it? I did a wall by mistake. Do you see it? I picked wall. I'm going to do a column. Remember that? And that column is going to be made out of 3 2x6s, select structural. And that then is going to come here and support half of my multi-loaded, multi-span beam, okay, which is this guy right here on the right, on the B. And that's it. And it passes by 61.9%. So the column 3 that was supporting Felipe and Rai was passing only by 39.6%. But the column 7 that's supporting only Rai passes by 61%, almost double, because it is supporting just half plus a little bit of the wall. Remember that? Does that make sense? And that same exercise goes all the way down. Ideally, this is a wall that's right here, a foundation wall, and we don't have to worry about any of that. But the goal is that you will track all these loads all the way down to the basement. So I hope this was helpful. It is late, and I commend each and every one of you for being here, for watching this video, for being present with me and understanding this. We're gonna get into much more fun stuff when it comes to the framing of the roof, the framing of how the eaves are framed, and all of those members. Then we're gonna do some funky things, like what if we have an overhang like this, with this wall like that, and this is outside? What if we have an overhang like this? What if we have these walls, funky things, voids, cool things that you all want to do as designers and future architects of the world, and architects. All right, so we'll see you on the next one. Like, share, and subscribe, and we'll stay in touch. And thank you, everybody, for staying here with me. Bye-bye.
Thank you.